Hello, beta. Good evening.
Good evening, sir.
Good evening, beta. Good evening.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening, beta.
Good evening, sir.
Good evening. So, how are we today?
All good, sir.
Okay, very good. Okay. So, beta, yesterday we started off with the ship's magnetism. And in ship's magnetism, we discussed two types of magnetism which is present in the ship, the hard iron and the soft iron. Just a minute.
Hello, hello, hello.
Okay, so we did the ship's magnetism yesterday. We saw two types of structure on the ship, hard iron and soft iron. Hard iron are those parts of the ship which are extensively worked upon when the ship is being built in the yard. And soft iron structures are those which are prefabricated, predominantly prefabricated, and not much working upon welding, cutting, hammering is done on them. So these soft iron structures, they attain induced magnetism, and the hard iron structures attain permanent magnetism. So we saw that permanent magnetism can be present in any oblique direction in the ship structure. So it is broken down into three components: fore and aft component known as P, Papa, outward ship component known as Q, Quebec, and the vertical component known as R, Romeo component. And these three components are corrected one by one separately. Then we saw that the induced magnetism can be present in horizontal soft iron. This could be fore and aft longitudinals, outward ship beams, and it could also be present in vertical soft iron. And the magnetism present on all these structures varies as the ship changes its latitude, ship changes its course. So it becomes a complicated and tricky combination of all these forces trying to deviate our compass. And the last thing what we did yesterday was the coefficients. I told you that the deviation which is present at any particular heading is a combination of some parts. And if we separate those parts, they are individually known as coefficients. Coefficient A is a certain part of the deviation, which has a certain property. We will see those properties now one by one. Coefficient B is another part of the deviation with a certain property. On some headings, it is maximum. On some headings, it is minimum. So that's how these coefficients are made up. Total, there are 5 coefficients. So this was what we did yesterday. And today we will be moving into the coefficients. We will first understand how a coefficient is generated. What are the structures? Is it generated by permanent magnetism or it is generated by induced magnetism? What are the structures in the ship which are responsible for generating that coefficient? So that's the first thing we'll see. Then we will see how does that coefficient generate the deviation. We will swing the ship all around and we will see how that coefficient generates the deviation. And then in the end, we will see how a coefficient is corrected. So as I told you yesterday also, each of these coefficients can be asked to us in a full-fledged 25 marks question. So ready to proceed ahead beta? चलें आगे coefficient A start करें?
हाँ सर शुरू करो.
Very good beta. Let's go. Let me put up the presentation. Let's now go into our first coefficient, that is coefficient A. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings and is further divided into two parts. These two parts are number one, real A, and number two, apparent A. Now, if you remember the formula which I had shown you, the formula for deviation, in that formula we saw that this coefficient A is not connected with the ship's course in any way. Indirectly, that means that whatever be the course of the ship or whatever be the heading of the ship, the value of coefficient A is not going to change. And you see exactly that is what the definition also tells us. Coefficient A is a deviation which remains constant in name as well as magnitude on all the headings. The vessel can continue to change its heading, and the deviation which is generated because of coefficient A does not change at all. It has two components and it can be divided into these two components. One is called as real A, another is called as apparent A. What is this real A part of the coefficient A? It is a constant deviation on all the headings caused by induced magnetism in unsymmetrical pairs of horizontal soft iron. I will explain this to you in detail by showing this kind of structure in the diagram. So for now, just understand it is caused by induced magnetism in unsymmetrical pairs of HSI, horizontal soft iron. So the cause of real A is the horizontal soft iron on board. The second part, which is called as apparent A. Apparent A is a constant deviation on all the headings, which is caused by factors other than the magnetic field. Moving ahead now, beta. Let me now show you the kind of structures which may generate coefficient A on a particular ship. Now we have seen that coefficient A is generated because of unsymmetrical pairs of horizontal soft iron. Now horizontal soft iron HSI can be present in two orientation. We can have a fore and aft horizontal soft iron, something like this one. This is horizontal soft iron in the fore and aft direction. And we can also have horizontal soft iron in the athwart ship orientation. You now see another horizontal soft iron which has a athwart ship orientation. So the first thing to note is that coefficient A require a pair. Pair means there should be a combination of fore and aft as well as athwart ship horizontal soft iron. The second thing which is required is that these horizontal soft iron should be unsymmetrical. Now what do we mean by unsymmetrical? If you look closely, the fore and aft HSI which we have is present only forward of the compass location. The circle which you see in the middle of the ship is representing the compass, the binnacle, and the HSI in the fore and aft orientation is only present forward of the compass and it is not there aft of the compass. This kind of a HSI is known as unsymmetrical HSI. Likewise, this athwart ship HSI which you see is present only on the port side of the compass and it is not present on the starboard side of the compass. So both these HSI are unsymmetrical. That means they are present only on one side of the compass and there is a pair present, means both fore and aft and athwart ship HSI are present. This kind of a combination, if it is present on a ship, will generate coefficient A. Now, Usually we do not see any kind of these structures on a normal merchant vessel. You will always have symmetrical HSI. So that is exactly the reason why coefficient A is absent on most of the normal merchant vessels. Moving ahead now, beta. Now let's try to understand if we have such a configuration of horizontal soft iron on board a ship, so these kind of structures are present. How do they result into a real A coefficient? Or in other words, how do they generate a deviation which is constant irrespective of the heading of the ship? Whichever heading the ship goes, the deviation generated by these structures remains constant and does not change. So let us try to understand it. Now this is understood by making a deviation diagram. For every coefficient, we will be making a deviation diagram like the one you see on the screen now. We have the ship on different headings: north, northeast, easterly, southeast, south, southwest, westerly, and northwesterly. So cardinal and intercardinal heading, the ship is shown on these 8 headings. And in each of these headings, we are going to analyze that how do these horizontal soft iron structures, it is an unsymmetrical pair of horizontal soft iron structures, they generate the deviation which does not change. So we will first try to understand how do these structures affect our ship, and second we will try to see that how does this effect remain same irrespective of the heading of the ship. So let's try to concentrate our attention with the ship on the northerly heading. The ship is on a north heading. You can follow the laser pointer. This is the diagram which we are going to see or understand in detail. Now the ship is on a northerly heading. We have these 2 soft iron structures. One a athwart ship beam which is only present on the port side of the compass, and we have a fore and aft longitudinal which is present on the starboard side only forward of the compass. It is not present aft of the compass. So we have combination number 1 which we saw in the previous slide, a unsymmetrical pair of horizontal soft iron structures. You see this big blue color rectangle on top. This represents the north magnetic pole of the earth. We are aware that the north magnetic pole of the earth has blue polarity. And you see this red color rectangle at the bottom. This represents the south magnetic pole of the earth, and we are aware the south magnetic pole has a red polarity. Now we know that the magnetic lines of force, they come out of the red pole and they go into the north pole. So the magnetic lines of force coming out of the red pole going into the blue pole. So in this particular diagram, you will see that the magnetic lines of force are going vertically upwards from the red pole to the blue pole of the earth, going vertically upwards like this. Now with the magnetic field of the earth going vertically upwards, it will affect both these structures. It will affect the fore and aft longitudinal also, and it is going to affect the athwart ship beam also. Now first thing to understand is that these are soft iron structures, so they do not have any permanent magnetism. There is no permanent magnetism in these structures. But being soft iron structures, they can get induced by the magnetism or magnetic field of the earth. Now the magnetic field lines are going vertically upwards. If you concentrate your attention to the athwart ship beam, this athwart ship beam is not oriented or aligned in the direction of the magnetic field. It is at right angles to the magnetic field of the Earth. And if you remember during induced magnetism, I told you that there is minimum induction or zero induction, negligible induction when the soft iron structure is misaligned with the inducing field. The inducing field in this direction is in the north-south orientation, and this authward-shaped beam is in the east-west orientation. The vessel is heading north, so the beam is in east-west orientation. So this beam is at right angles to the inducing field or the magnetic field of the Earth. Now, being at right angles, no induction happens. No magnetic field induction happens here, and the outward shaped beam does not acquire any magnetism. There are no poles which are generated. Let's now concentrate our attention to the fore and aft longitudinal. The fore and aft longitudinal, if you look carefully, is aligned exactly in the same direction in which the Earth's magnetic field lies. The magnetic field lines are in the north-south orientation. The fore and aft longitudinal is also exactly in the north-south orientation. So the fore and aft longitudinal is perfectly aligned with the magnetic field. And this tells us that there will be maximum induction in the fore and aft longitudinal. Maximum induction. So we know the fore and aft longitudinal having maximum induction will become a strong magnet now. Let us now understand the direction of the poles which are generated. We see the magnetic field lines are coming out from the red pole of the Earth and going into the blue pole. So this tells us that these magnetic field lines will be entering into the aft end of the longitudinal. If they are entering into the aft end of the longitudinal, wherever the lines of force enter, that end gets a blue polarity. Wherever the magnetic lines of force are entering, that end of the magnet has a blue polarity. So that's why you see the aft end of the fore and aft longitudinal has a blue magnetic pole. And these lines of force going from south to north will be coming out from the forward end of the longitudinal, the forward end. Since they are coming out of the forward end of the longitudinal, you will see that the forward end of the longitudinal acquires red polarity. So this is the reason why you see in the diagram, the aft end of the longitudinal has blue polarity and the forward end of the longitudinal has red polarity. So we now understand the different poles generated on the fore and aft longitudinal. Now we have understood the induction or induced magnetism of the horizontal soft iron structures by the Earth's magnetism. Let's now try to see that at different headings, what is the deviation which is generated because of this induced magnetism? So as you can see in the diagram, at every heading, they indicate to us that it is a easterly deviation. You see north heading, northeast, easterly, southeasterly, southerly. On all the headings, they are denoting that the vessel has a easterly deviation. And in the definition of coefficient A, we have seen that it generates a constant deviation irrespective of the heading. So we will try to see now how does this deviation remain constant over all the headings. Let's first of all try to understand how this easterly deviation is generated with the ship on northerly heading. So what I'm going to do is I'm going to zoom in into this diagram with the ship heading north. We are aware that we have a fore and aft longitudinal and a outward ship beam. There is no induction on the beam right now because it is at right angles to the Earth's field, and there is maximum induction in the fore and aft longitudinal. So let's now try to zoom in into this. So here on the left side, you see a zoomed in diagram with the ship heading north. Let's first make the magnetic compass on this ship. Now we know the magnetic compass is basically a magnet, and the end which points towards the north is the red end of that magnet. So let's show our magnetic compass. You can see it here. The north end of the magnetic compass is having a red polarity. You see the red color, and the south end is having a blue polarity. So this arrow which you see in the zoomed in diagram of the ship now represents the magnetic compass. And we have a longitudinal which is to the starboard side of the compass, and it is forward of the compass location. It is not present aft of the compass location. So you can see this longitudinal in the zoomed in diagram now, and it is to the starboard side of the compass and is extending to forward of the compass. Now we have already seen that this particular end, the aft end of the longitudinal, acquires a blue pole, and the forward end of the longitudinal acquires a red pole. This is a soft iron structures, and these poles are acquired as induced magnetism, which are generated by the magnetic field of the earth. Now whenever we bring a magnet close to our compass, every magnet has two poles, a red and a blue pole. We cannot have a single pole in a magnet anywhere. Even if you break up a magnet, the broken ends immediately acquire the polarity. You cannot have a single pole at any point. Now whenever you bring a magnet close to the compass, it has both the poles, the red as well as the blue. Now which of the poles is going to affect the compass? Always, in all the conditions, that poles affect the compass which is closer to it. Because as you go far away from the pole, the magnetic field or its strength or its power reduces. It is inversely proportional to square of the distance. Means if you increase the distance by twice, the magnetism or magnetic field strength of the pole goes down by 1/4. So whenever you bring a magnet close to the compass, that particular pole which is closer with respect to the other has its effect on the compass. Now in this particular case, the longitudinal is having two ends. One of the ends is very close to the compass, which is having a blue polarity, whereas the other end, for clarity I have exaggerated a bit and taken it out of the ship's hull. So the other end of the longitudinal is close to the bow of the ship, which is much farther away as compared to the blue pole. So in this case, blue pole is the one which is going to have its effect on our magnetic compass. Now, how does this blue pole affect our compass? The effect of this blue pole onto the red end, that is the north end of the compass, will be attraction. Because we are aware that opposite poles of a magnet attract each other. So this blue pole of the fore and aft longitudinal is going to attract the north end of our magnetic compass or magnetic needle. So when it attracts the north end towards it, the compass is going to deviate to the right side. Looking at the diagram, it is going to deviate to the right side, and that is easterly side. With the vessel heading north, the right side is easterly direction, so a easterly deviation is generated. Also you can see this blue end is also going to interact with the south end of the compass. The south end of the compass also has a blue polarity. Now we know that the same poles of the magnet repel each other. So this blue pole of the longitudinal is going to repel the blue pole or the south end of our magnetic compass, again generating easterly deviation. The compass needle is going to swing clockwise, which is easterly deviation. So that is why you see they have mentioned here as easterly deviation. Any doubts coming up to here, beta?
So in this case, this forward and aft longitudinal is on the starboard side. If it was on the port side, then the deviation will be westerly.
That's correct, beta. That's correct. Now I have shown you one particular combination. There is a possibility of other combinations also being present on the ship which can generate coefficient A. So in some other combination, it is possible that a westerly deviation may be generated. But in that case, all the headings, the deviation will remain westerly.
Yeah, okay. Okay, sir.
Okay, great. So let's move ahead, beta. Let's try this out on other headings also. Let's now take the ship on a easterly heading and understand the deviation generated. Now on the easterly heading, we can see that the fore and aft longitudinal is now at right angles to the magnetic field of the Earth. The Earth's magnetic field lines coming out from the red pole going into the blue pole are going vertically upwards. The fore and aft longitudinal is at right angles, so no induction is generated on the fore and aft longitudinal. On the other hand, the outward ship beam is now perfectly aligned with the magnetic field of the Earth, thus generating maximum deviation. So let's now zoom into the easterly heading diagram and see the effect in detail. You can see the outward ship beam shown in the diagram. I have taken the outer end slightly outside the ship structure to make it more clear and easy for understanding. The fore and aft longitudinal is not shown in the diagram because there is no induction and no poles are generated. Now magnetic field lines are entering into this particular end, the south end of the outward ship beam, giving it a blue polarity. Wherever the lines enter, the soft iron acquires a blue polarity. And the lines are coming out from the north end of the outward ship beam, giving it a red polarity. Now we have a blue pole to the east of the compass. The compass needle points in the north direction. Vessel is heading in the easterly direction. So this blue pole, which is to the east of the compass needle, attracts the red end of the compass needle towards it. The needle is pivoted at the middle at this particular point here. So it swings clockwise towards the blue pole shown by this arrow, generating a easterly deviation. Also, this blue pole repels the blue end of the compass needle, and this also adds on to the clockwise swing or the easterly deviation generated in the compass needle. Is it clear, beta? Any doubts on easterly heading?
No, sir. Good to go, sir.
Very good, beta. Great. Now let's move on to northeasterly heading. So northeasterly is little tricky. It's little complicated. So let's try to analyze the northeasterly heading now. Now let's see a third scenario with the ship heading in the northeasterly direction. So with the ship heading in the northeasterly direction, how does the deviation behave? Let's zoom into this diagram of the ship. So on the left side, you see the zoomed in diagram of the ship. We have the compass as usual placed in the center line. Irrespective of what is the direction in which the ship is heading, the compass needle is always going to point north and south. The north end will be the red end of the compass and the south end will be the blue end of the compass. Now we have a longitudinal, fore and aft longitudinal to the starboard of the compass. So you can see on the starboard side, we have a fore and aft longitudinal, which is only forward of the compass. It is not there aft of the compass. We also have a outward-ship beam. The outward-ship beam is forward of the compass and only to the port side. You can see the outward-ship beam is only to the port side of the compass. It is not present on the starboard side. Now I have taken the far ends of the longitudinal and the beam out of the ship's hull just to make the picture a little more clear and easy for understanding. Now in this case you see the Earth's magnetic field coming from south to north is going to induce both these structures because both of these structures are now at a 45-degree angle to the Earth's magnetic field. They are neither fully aligned nor misaligned. They are partially aligned with the magnetic field of the Earth, so there will be partial induction on both these structures. That is the longitudinal as well as the beam. Partial induction on both of them. So the poles generated will have partial power. And now you look carefully. The blue pole is generated in the longitudinal as well as the beam, and this is the pole which is closer to our compass. The red poles generated are far away from the compass. So blue poles are the one which are going to affect our compass. Now the blue pole of the outward-ship beam is closer to the red end or the north end of the compass, and it is going to attract the compass towards it. Whereas the blue pole in the longitudinal is close to the south end of the compass, which is again blue, and both being the same polarity, they are going to repel each other. And you will see, even though there are two poles, they are both trying to swing the compass in the clockwise direction again. So you see, the compass has to swing clockwise again, generating easterly deviation. Now one doubt may arise that since there are two blue poles now, the deviation generated will be more powerful, but that is not the case. Reason being, even though two poles are generated, but both of them have partial power. Why the power is partial? Why their strength is partial? Because they are not perfectly aligned with the magnetic field of the Earth. Both the longitudinal and the outward-ship beam are partially aligned, making these poles partially powerful. So when both these poles add up, they generate the same easterly deviation which was generated on 000 heading and 090 heading. So you can see, irrespective of the heading on which the ship is, the deviation generated remains the same. Is that clear, beta? Any doubts coming in?
No, sir, clear.
Very good, beta. Great. Now in the book, beta, these diagrams which you see on the right hand side, the diagrams are very small and crammed up. So looking at these diagrams, sometime you may get confused. How is this deviation generated? Also the compass is not colored in the book explanations. So that's why I have zoomed in. You can see the structures clearly and you can also see the poles of the compass. That makes it very clear how the deviation is generated. So now the same fundamental can be applied on all the other headings, and you will see that at every heading the deviation generated is easterly deviation. This is what we call as real A. Great, let's move ahead now.
Sir, can you show on the southeasterly heading also, sir? Little bit confused when I'm making here.
Okay. मेरे पास यहाँ तो नहीं है, बनाना पड़ेगा. आप एक बार ट्राई करना बेटा, ट्राई मेकिंग इट योरसेल्फ. यही जो डायग्राम है, टेक दिस शिप टू द साउथ ईस्टर्ली हेडिंग, साउथ वेस्टर्ली, एंड ट्राई डूइंग इट. अगर फिर भी डाउट आए तो मुझे कल बताना.
ओके सर, ओके सर, थैंक यू.
ओके ओके. Now let's move on to the correction of real A. How do we correct this coefficient? The correction of real A is generally not attempted, not done. The reason for it is Number one, it is very rare on a normal seagoing merchant ship that a coefficient A will exist, because these kind of soft iron structures are not present on the ship. Whatever soft iron structures are present, they are symmetrical about the compass location. Even when it is present in some ship, it is likely to be very, very small. So this is the reason why we do not attempt the correction of real A. What is done then? Since the deviation generated is constant on all the headings, it can be applied as an index error. So you will see that on a ship where real A is present, the real A value will be mentioned separately in the deviation card. Like, let us say, for example, the deviation card will tell you that the real A correction or index error correction is 1 degree east. So whatever deviation you obtain from the curve, you add 1 degree east to that deviation and it will give you the resultant deviation. So deviation being constant on all the headings, is it applied as a index error and the real A is not generally corrected. Moving ahead now, beta. Now the second component of coefficient A, which is known as apparent A, is basically the constant deviation on all headings caused by factors other than the magnetic field. So any reason, any cause other than the magnetic field which leads to a constant error on all the headings will come under apparent A. There can be numerous reasons for generation of apparent A. Some of the examples, some possibilities which could lead to this kind of an error. You can have the magnetic needles of the card not parallel to 180 degree direction of the card. Now this is a manufacturing defect. You can visualize a card is being printed. The magnets are to be fitted exactly in the 000180 direction. But if during the construction of the card, the magnets are fitted slightly at an angle, let us say 002 and 182 direction, so there will always be a slight error which the compass will show. This has got nothing to do with magnetism, so this falls under apparent A. That's a manufacturing defect in the card. Sometimes we see there is a lubber line which is fitted on the repeater. If the lubber line is not parallel to the ship's fore and aft line, so whenever you read that lubber line to get the heading of the ship, there will be a constant error. This has got nothing to do with the magnetism, and it's also a manufacturing defect, so it falls under apparent A. Other reason could be constant error in observing the bearings when the compass is initially adjusted. For example, there could be an index error in the azimuth mirror leading to wrong deviation card. So when that wrong deviation is applied, you will get an error. So that's also a non-magnetic reason. Further reasons could be error in computing the magnetic bearing when the compass was adjusted, rapid swinging of the vessel when observing the bearing for compass adjustment. It is recommended that whenever we are doing the compass adjustment, the vessel should not be swung rapidly. It should be steadied on a particular heading before noting down the deviation. Or R angles worked out wrongly leading to error in the calculated bearing. We usually obtain the compass error by using the azimuth, calculating the azimuth by ABC method. So if the method has been worked out wrongly, it will lead to a wrong deviation being noted down. And if we use that wrong deviation, it will give us wrong bearings or wrong heading of the ship. So there could be many other reasons also. Any reason other than magnetism which leads to a constant error on all the headings falls under the category of apparent A. Moving ahead now. Now, how do we calculate the coefficient A for the correction purpose? The value of coefficient A can be easily obtained as the mean of deviation on at least 4 equidistant headings. What does that mean? Let us take the ship on a northerly heading and note down the deviation. Let's now take the ship on a easterly heading, note down the deviation, then southerly heading and westerly heading. So all the 4 cardinal headings, we swing the ship, take it to 4 cardinal headings, and we note down the deviation on these 4 headings. Now, once you take a mean of these 4 deviations, it gives you the value of coefficient A for that particular ship. Practically, this is done using 8 deviations on cardinal and intercardinal headings. Taking this value in 8 deviations gives you more accuracy. So practically we use the deviations on cardinal and intercardinal headings and take a mean. Now you can easily test out this method or try out this method using this formula. This is the same formula which I showed you. Deviation is equal to coefficient A plus B sine cos plus C cos cos plus D sine 2 cos plus E cos 2 cos. So in this formula, if you put the cos as 0, 0, 0 and get the result, then second time you put the value as 90, third time you put the value as 180, fourth time you put the value of cos as 270. Now once you get the answers and you take a mean, you will see that all the other coefficients B, C, D and E will get cancelled out. The only coefficient which will remain is coefficient A. So any doubts in coefficient A now, beta? Very good, beta. Great. Very good. So this was coefficient A. Now tell me, go ahead, Amit. You want to ask something?
सर ये जो दूसरा फॉर्मूला बताया, फॉर्मूला इज जस्ट फॉर चेकिंग वेदर द कोएफिशिएंट इज एक्यूरेट और नॉट, बट अदरवाइज व्हेन फॉर प्रैक्टिकल ऑल प्रैक्टिकल पर्पसेस we go on all 8 headings and take out the mean.
Yeah, that's right, beta. That is what is practically done. And the formula is just to prove that that method is correct.
ठीक है सर, ओके. एंड सर ये लाइक यू एक्सप्लेन 25 मार्क का क्वेश्चन आता है, तो वही वो इसका डेफिनेशन लिख के जो आपने वो इतना वो जो बड़ा डायग्राम बताया, ये सारा करके this much should do, right?
That's correct, beta. That's correct. The first thing will be the definition, that it has 2 parts, real A and apparent A. Second, make a diagram of the structures. You have these 2 structures. And third important part is making this deviation diagram, beta. Okay, so make this deviation diagram, show the deviations on all the headings. And next would be the correction. So once you do this much, that completes the 25 marks, beta.
Sir, regarding this blue and red marking, we do it on the pen showing like B and R. That will be enough, right?
Yeah, that's correct, beta. Good, you raised that point. Now, this blue and red indication which you are seeing here, now beta, unfortunately, you are not allowed to use the red pen in exams. Red color is basically reserved for invigilation. Green is reserved for rechecking. So you cannot use the red color. So what you can do is you can put, as you said, Bravo and Romeo representing blue and red. So that can be used, beta. B and R you can put it and explain. Okay, all right. Great, beta. Go ahead, beta.
Sir, at the end you have just mentioned that regarding that formula,
right.
When we take the mean, all other coefficients will be cancelled and only A will be there.
Yes.
Explain one more time. I didn't get that one.
Okay.
How the other coefficients are cancelled.
Okay, I'll tell you how does that happen. Now beta, if you put 0 in this formula, the course has 0. Okay, you see the second part, B sine course, sine 0 is 0, so B will get cancelled out. Okay, and what about C? Cos 0 is 1, so you will have plus C in that formula, right?
Yes.
Now when you put 180 beta, when you put 180, you see the cos 180 is going to become minus 1.
Okay.
So that plus C and minus C are going to get cancelled. Okay.
Okay.
Similarly, B, D, and E, Bravo, Delta, Echo, all of them are going to get cancelled if we use these 4 cardinal courses and calculate their value and add them and take a mean. Only thing what will remain is A.
Okay. Yeah. Okay, sir. Now understand.
Okay. Great. Very good.
Sir, I have
Go.
one question.
Bolo beta.
Sometimes yearly when we are swinging the ship on board and calculating deviations, so it is basically we are getting the coefficient A. We are making a deviation part on board the things. It's basically coefficient A, or what is it?
नो बेटा नो, जब आप शिप को स्विंग करते हो तो बेसिकली आप कोई भी कोफिशिएंट कैलकुलेट नहीं कर रहे हो. You are just swinging the ship and noting down the deviation, and you are making a fresh deviation card. That's all.
Okay. So it has nothing to do with this coefficients.
No, it has got nothing to do with coefficients. Coefficients is much more deeper. आप तो सिर्फ बेटा डेविएशन को ऑब्जर्व कर रहे हो और एक नया कार्ड बना रहे हो. बट जब कंपास एडजस्टर आपके शिप पे आएगा, कंपास एडजस्टर नॉट ओनली मेक्स ए डेविएशन कार्ड बट ही आल्सो हैज टू पुट द करेक्टर्स.
करेक्ट.
अब जैसे आपको कंपास एडजस्टर शिप पे आता है, उसे 4.5 मैग्नेट्स डालने हैं, तो ही हैज टू इवेल्युएट कि मैं कितने मैग्नेट्स डालूं, 1 पेयर डालूं, 2 पेयर डालूं और कौन से स्लॉट में डालूं. उसे आपकी कंपास के दोनों तरफ स्फीयर्स लगाने हैं, सॉफ्ट आयरन स्फीयर्स. सो ही हैज टू सी कि मैं स्फीयर्स को किस पोजीशन में लगाऊं. शैल आई ब्रिंग देम क्लोज टू द कंपास और फार अवे फ्रॉम द कंपास. उसे फ्लिंडर बार लगानी है तो ही हैज टू चेक कि मैं फ्लिंडर बार की लेंथ कितनी रखूं, हाउ मच लेंथ शुड आई मेंटेन. ये सारी चीजें आपको पता चलेंगी व्हेन यू कैलकुलेट द कोफिशिएंट्स, because these coefficients will give you an idea what is the magnitude of the correction required. So usually as navigators we don't do this. हम compass adjuster को बुलाते हैं and he does that. Or many of the companies now they do it over email or phone also. So he checks the deviation generated and he sends you that please arrange the correctors in this particular way and that gets done. So हम लोग usually इतना depth में नहीं जाते हैं.
Okay sir, understood.
Okay, all right. अब मुझे एक बात बताओ बेटा, कोफिशिएंट ब्रेवो पे जाने के लिए रेडी हो? ब्रेक तो नहीं लेनी? इज इट ओके? कंफर्टेबल? कैन वी गो अहेड?
Yes sir, please go ahead sir.
Very good.
Sir, I have a doubt regarding this compass card adjusting. Can I ask?
बोलो बेटा. Yeah, please.
So actually, if you're adjusting the compass in the northern hemisphere and fixing a card in the northern hemisphere, when the ship comes down to the southern hemisphere, the deviation doesn't match us most of the time.
Yeah, right.
So, so for example, on board when we have wetting or some other things, when you're obviously in the other hemisphere, is there some other way that to match, do some adjustment in the compass to match it?
Very difficult, very difficult. Basically, बेटा दो reasons हैं. While you are changing the hemisphere, जब इक्वेटर क्रॉसिंग होती है ना, तो 2 रीजंस हैं जिनकी वजह से आपकी डेविएशन कार्ड जो है इट gets redundant and the deviation changes. One reason is that your compass is not properly corrected. Okay, not well corrected. If the compass is not well corrected and you change the hemisphere, you see when we change the hemisphere, the direction of the Earth's magnetic field changes. North hemisphere, the lines are going down. South hemisphere, the lines are coming up. So all the vertical structure will have their poles reversed. If the mast was having a blue pole on top, you change the hemisphere, you will have a red pole on top. So this is the reason why the deviation may get disbalanced and your deviation card may be inappropriate. So one reason, first reason, compass is not properly corrected. And the second reason, beta, ये हम बाद में pick up करेंगे once we do the coefficients. It is known as healing error correction. This healing error is the main cause of change in deviation when you change the hemisphere. Hemisphere change करने से एक healing error ऐसी correction है जो disturb हो जाती है and it needs to be redone again. Okay. I am not sure अगर आपने कोई सेल किया हो old masters, fresh young masters usually don't touch the binnacle and the correctors. But अगर किसी ने note किया हो ये, if you do equator crossing, you may see some master may go to the binnacle. He takes out some magnets from the binnacle, from the healing error bucket basically, turns them. These are permanent magnets, so they have blue and red end, turns them and then puts them back again. Has anybody seen that kind of thing happening?
No, sir.
No. So silence tells me you are all sailing with.
Sir, heard about it but not seen.
Okay, all right. Okay.
We are seeing that the number.
डेविएशन कार्ड ही शिप पे फर्जी बना के रखते हैं सर. ये तो जो आप बोल रहे हो तो अलग ही चीज है.
Okay, all right. So पुराने टाइम में ऐसा किया करते थे. So I will tell you that in detail why it is done, what was the reason or need for that. वो हम तब करेंगे when we go to the healing error part. Okay.
Yes.
और बताओ बेटा, और कोई doubts? Okay, great, very good. So let's go into coefficient B beta. B pick up करते हैं. Let me go back to the presentation.
सर ये जो फॉर्मूला आपने बताया था इसमें अगर कोर्स 0 डाल रहे हैं वो तो ठीक है, लास्ट में हमारा ए ही बचेगा 0, 90, 180, 270. बट व्हाट अबाउट द इंटरमीडिएट लाइक 45?
ओके, डोंट बेटा, हमने तो 4 इक्विडिस्टेंट हेडिंग्स लेनी है ना. सो आप सबसे इजी वाली नॉर्थ, ईस्ट, साउथ और वेस्ट ले लो. दैट विल मेक इट वेरी मच क्लियर. अब अगर आप बीच की भी कोई लेना चाहते हो, यू वांट टू टेक इंटर कार्डिनल.
हाँ सर, इंटर कार्डिनल.
ओके, इवन इफ यू टेक इंटर कार्डिनल बेटा, साइन ऑफ 045 एंड साइन ऑफ 225, they will be exactly opposite of each other and they will cancel out each other. Do you agree?
So sine of 45 and sine 225. Okay.
Exactly. They will be equal in magnitude and opposite in direction. One will be plus, another will be minus. So they will cancel out each other when you add them.
सर बट इसमें जैसे फॉर्मूला में डालेंगे ये तो ये हो जाएगा ना sin 45 और sin 90.
नहीं बेटा, यू sin 45 होगा ब्रेवो में, 90 होगा डेल्टा में. करेक्ट?
हाँ करेक्ट सर, करेक्ट.
So delta will also get cancelled.
अच्छा ठीक है सर.
Okay, it will also get cancelled. Do this exercise. Put the course as 0 and calculate this. Then you put it at 90. Then you put it at 180, 270. You can do this with intercardinal.
वो 0 आ रहा है, वो कर लिया, वो 0 आ रहा है.
तो 45 से भी कर लो, same thing. You have the calculator. Okay, all right. So moving on to Bravo beta. We are going to Bravo now. Now, how is this component generated? Let us see. Now let's move on to the second coefficient, that is coefficient B. The definition says coefficient B is the maximum value of the semicircular deviation which varies as the sign of the compass course. Now in the formula which I gave you, in that particular formula, what is that part which is proportional to or which varies as sine of the compass course? It is the second part of the formula, that is B sine course. Now the maximum value of that deviation is what is coefficient B. So you see this definition has been picked up, or you can easily remember this definition basis the formula. Coefficient B is the maximum value of the semicircular deviation which varies as sine of the compass course. That part of the deviation which varies as sine of the compass course, the maximum possible value what it can have is what is coefficient B. Now, what is the meaning of semicircular deviation? Now we know one circle is 360 degrees. So if a deviation carries the same name over the entire 360 degrees, if it is east and it remains east for the vessel heading on entire 360 degrees, it is called a circular deviation. A deviation which is of one single name for a semicircle, that is 180 degrees, and in the other semicircle, the remaining 180 degrees, it gets a opposite name. It is called as a semicircular deviation. To give you an example, let us say on a particular ship, you observe the deviation from heading north to south. It is easterly deviation. And when the ship heads from south to southwest, that is 180, 190, 270 up to 360 in the southwest and northwest quadrant, the deviation is westerly. So you see now for 180 degrees, the deviation was east. For the next 180, it has changed to westerly direction. Such a deviation is called as a semicircular deviation. Now, if a deviation changes after every 90 degrees, for the first quadrant, the northeast quadrant, the deviation was easterly. For southeasterly quadrant, the deviation becomes westerly. For southwesterly quadrant, it again easterly, and for northwesterly quadrant, it becomes westerly. Means it changes after every 90 degrees. It is known as a quadrantal deviation. So semicircular deviation means that for 180 degrees out of the total 360, it will have one particular name, either east or west. And for the remaining 180 degrees, the name is going to be opposite to this one. So that is the meaning of the semicircular deviation. The causing factor for this particular coefficient is the horizontal fore and aft component of the ship's magnetic field. Now, how is this component generated? Let us see. The horizontal fore and aft component of the ship's magnetic field is caused or generated by permanent magnetism of the ship as well as induced magnetism of the ship. So the contributing factor for coefficient B are both permanent magnetism as well as induced magnetism. The part of coefficient B generated by permanent magnetism is called permanent B, or in short PB, Papa Bravo. And that part of the coefficient B which is generated by induced magnetism is called induced B, or in short form IB. Let's now see the cause of permanent B on a ship. Now we are aware, concentrate your attention to the diagram, first diagram on the left hand side, where the laser pointer is right now. Let's assume that this ship is being built in the yard on a northerly heading. If it is built in a northerly heading, the lines of force will be entering from the stern of the ship and leaving from the bow of the ship, giving the stern a blue polarity and the bow a red polarity. Now, if the ship was built on a southerly heading, then in that case, you will have a blue bow and a red stern. Now, these poles which are generated are permanent poles. So depending upon whether the ship was built on a northerly heading or a southerly heading, you will have a blue bow or a red bow. Now, when the ship has magnetism in this particular way, it has a blue bow and a red stern. How does this magnetism affect our compass? If you look carefully, this is the permanent magnetism of the ship in the horizontal fore and aft direction. What causes permanent B? So let us see its effect on our magnetic compass. So up to here is clear, beta?
Yes, sir.
Very good. So we are going to pick up one of these shapes and we are going to see what kind of deviation does that generate. Let's see. Now this is a diagram which is showing us, this is the deviation diagram for coefficient B. It is showing us a shape which has a blue bow. You see everywhere at the bow we have a blue pole, and this ship is having a red stern. So this tells us that this particular ship was built on a southerly heading. So just now, as we saw in the previous slide, a ship which is built on southerly heading will have a blue bow, the lines of force will be entering there, and a red stern. Now, how does this permanent magnetic field of the ship in the horizontal direction, fore and aft direction, going to affect our compass? Let us see it heading by heading. Now, with the ship heading in the northerly direction, we have a blue bow and we have a red stern. The compass needle is shown in the middle of the ship. We know that the end of the compass needle pointing towards north is the red end and the one pointing towards the south is the blue end. So we have the compass needle. Now when the ship is heading north, these blue and red poles of the ship are exactly north and south of our compass needle. So being exactly north and south of the compass needle, they do not generate any deviation at all. So there is no deviation on the northerly heading. Let's now assume the vessel has moved to a northeasterly heading in this particular direction. Now the blue pole has gone northeast of the compass, and this blue pole is going to attract the red pole of our compass, and the compass is going to deviate towards east. So you have a easterly deviation. The same thing happens with the red pole. The red pole of the ship, permanent magnetism, red pole of the ship has gone to southwest of the compass, and it attracts the blue end of the compass towards it, giving the compass a easterly deviation. So you can see now on a northeasterly heading, a easterly deviation is generated. When the ship goes to a easterly heading, 090 heading, now you see the blue pole is to the east of the compass and the red pole is to the west of the compass. They are at right angles to the poles of the earth, and now in this location they generate maximum deviation. The blue pole at the bow attracts the north end or the red end of the compass towards it, and the red pole at the stern attracts the south end of the compass towards it, giving it maximum easterly deviation. When the ship heads in a southeasterly direction, In a southeasterly direction, the blue bow goes to southeast of the compass, and this blue bow repels the blue end of the compass needle, that is the south end of the compass needle. Similarly, the red pole of the ship at the stern repels the north end of the magnetic needle, again giving it a easterly deviation. But the magnitude of the easterly deviation starts to reduce now because the ship's poles are coming in line with the magnetic field of the Earth. Maximum deviation is generated when the ship's poles are at right angles to the magnetic field of the Earth, which happened on easterly heading. And minimum deviation is generated when the poles are aligned with the poles of the Earth, which happened on northerly heading. If ship pole and Earth pole are aligned, there will be no deviation at all. And if the ship's poles and Earth pole are at right angles, there will be maximum deviation. So that's why in the southeasterly heading, the deviation is reduced now, but it is still easterly. When the ship goes on southerly heading, even though the blue pole is closer to the blue end of the compass needle and the red pole is closer to the red end of the compass needle, they are still not able to generate any deviation. The red and red poles are repelling, blue and blue poles are repelling, but the strength of the poles of the ship is much weaker as compared to the strength of the Earth's poles. So that is why they are not able to turn the compass needle by 180 degrees. If the ship's field was more powerful, it would turn the compass needle by 180 degrees and the needle will start pointing south. But since these poles are much weaker, the magnetism of the ship is much weaker as compared to the magnetism of the Earth, they are not able to generate any deviation at all. When the ship goes on southwesterly heading, you can now see that the blue pole at the bow repels the blue end of the compass needle. Similarly, the red pole at the stern of the ship repels the red end of the compass needle, generating a westerly deviation. When the ship is heading in the westerly direction, this westerly deviation becomes maximum because the poles of the ship are at right angles to the poles of the Earth. The blue pole to the west of the compass needle attracts the red end towards it, generating a westerly deviation. Similarly, the red pole of the ship at the stern attracts the blue end of the compass needle, generating a westerly deviation. So maximum westerly deviation is generated on westerly heading. With the ship going on northwesterly heading, the deviation is still westerly, but the magnitude is reduced because the ship's poles are now coming in line with the magnetic poles of the Earth. Coming back to north, the deviation becomes 0. So you see, from 000 to 180, the deviation was easterly, and from 180 to 360, the deviation was westerly. This is what we mean by a semicircular deviation. For one semicircular, the deviation has a single name. For another semicircle, the deviation has a opposite name. So therefore, it is called as a semicircular deviation. Go ahead, beta. Go ahead. Any doubts, beta? Please go ahead.
Sir, this is represented in the southern hemisphere.
One by one, beta.
Yeah, so this diagram is presented in southern hemisphere or northern hemisphere?
Okay, it is applicable to both the hemispheres, beta.
But if the magnetic lines are coming from the red bar, then it should enter in through the ship's stern, right? On the first diagram, the blue
Okay,
pole
beta.
should be down.
Okay, try to understand and visualize. The change which happens when you change the hemisphere is in the vertical orientation of the magnetic field lines. vertical orientation. Southern hemisphere, they are coming out. Northern hemisphere, they are going down. But you see their horizontal component, H or HF component. The H or HF component is always from south to north, whether you are in the southern hemisphere or northern hemisphere. And our needle here is in the horizontal plane. So we are only concerned about the horizontal component or the HF component. The Z component is not playing any part in deviation at all.
सर वो सदरली हेडिंग में क्यों चेंज नहीं हुआ समझ नहीं आया सर.
ओके बेटा, पहला डाउट क्लियर हुआ?
या ओके सर.
ओके ओके, अब आते हैं बेटा सदरली हेडिंग पे. सदरली हेडिंग पे ये चेंज क्यों नहीं हुआ बेटा? डेविएशन जनरेट करने के लिए द शिप्स पोल्स हैव टू बी मिसअलाइंड फ्रॉम द पोल्स ऑफ द अर्थ. Now when you are on southerly heading, you see the ship's poles are exactly in line with the poles of the earth. अगर हमें नीडल को ईस्टर्ली या वेस्टर्ली डेविएशन जनरेट करवानी है तो कोई साइडवेज फोर्स भी तो चाहिए बेटा. हमारे जो शिप के पोल्स हैं, दे आर अपोजिंग द पोल्स ऑफ द अर्थ बट दे आर वीकर, सो देयर एंटायर इफेक्ट इज कैंसल्ड, काउंटरएक्टेड. ओके, इट इज समथिंग लाइक, अगर आप इसे समझ सको तो आई विल गिव यू अनदर प्रैक्टिकल सिचुएशन. लेट अस से आप किसी पर्टिकुलर कोर्स पे जा रहे हो एंड देयर इज ए करंट कमिंग फ्रॉम द स्टर्न और कमिंग फ्रॉम द बाव. नाउ अगर करंट आपके बाव से आ रहा है तो वो सिर्फ आपकी स्पीड को रिड्यूस करेगा, आपके CTS और CMG में कोई डिफरेंस नहीं आएगा. ओके, करंट अगर स्टर्न से आ रहा है वो सिर्फ आपकी स्पीड को इंक्रीज करेगा, बट देयर विल बी नो डिफरेंस बिटवीन CTS एंड CMG. नाउ ऑन द सेम हैंड, अगर करंट आपके बीम से आ रहा है, ओके, अगर पोल्स जो हैं वो ईस्ट वेस्ट डायरेक्शन में चले जाते हैं या करंट आपके बीम से आ रहा है, it will generate maximum difference between CTS and CMG.
समझ में आया सर. अब
समझ गए? वेरी गुड बेटा, ग्रेट. सो एक चीज और आपको बताता हूं, उससे भी हो सकता है क्लैरिटी आ जाए. जो ये शिप के पोल्स हैं बेटा, शिप के पोल्स, इनका नॉर्थ साउथ कंपोनेंट जो है, नॉर्थ साउथ कंपोनेंट, वो डेविएशन को बिल्कुल इफेक्ट नहीं करता. इनका ईस्ट वेस्ट कंपोनेंट जो है वो डेविएशन को मैक्सिमम इफेक्ट देता है. सो शिप के पोल जितना कंपास नीडल के ईस्ट या वेस्ट में जाएंगे उतना ही ज्यादा डेविएशन जनरेट होगी.
समझ गया सर. थैंक यू सर.
वेरी गुड बेटा, ग्रेट. सो लेट्स मूव अहेड. नाउ अनदर important thing which you can see from this diagram is that these poles of the ship also affects the directive force at the compass location. What is this directive force? Directive force is the strength of the magnetic field at the compass location which makes it point towards the north direction. Now with the vessel heading on the northerly heading, you can see that the poles of the ship are matching with the poles of the earth. The Earth's north pole is a blue pole and the ship structure also has a blue pole north of the compass. So this blue of the earth and blue of the ship are adding up, increasing the magnetic field. Similarly, south of the compass we have the red magnetic pole of the earth and the ship's pole is also red. So Earth's red and ship's red, they also add up to the directive force. So in this particular heading, northerly heading, the directive force is increased to its maximum. When the ship goes on easterly heading, in the easterly heading, the red and blue poles of the ship are neither north of the compass nor south of the compass. They are exactly east-west of the compass. Being east-west of the compass, they do not have any effect on the directive force. So the directive force is unchanged at this particular location. Now with the ship heading in the southerly direction, you see now the poles of the ship are opposite to the poles of the earth. South of the compass, we have the blue pole of the ship and the red pole of the earth. North of the compass, we have the red pole of the ship and the blue pole of the earth. So with the ship pole and the earth pole becoming opposite, the directive force is reduced. So there is a maximum reduction in the directive force with the ship heading in the southerly direction. So is that also clear, beta? Any doubts coming in? Very good, beta. Great. So these are the two items which are explained in this deviation diagram. One is the deviation generated. Another is the effect on the directive force. Let's move ahead now. Now moving on to the correction of coefficient B. Coefficients are always corrected on the heading on which they produce maximum deviations. Now the first thing which the compass adjuster needs to know is on which heading should I correct coefficient B. So we should always remember coefficients are always corrected on the heading on which they produce maximum deviation. Now coefficient B produces maximum deviation on easterly or westerly heading. So that is where it is corrected. For the coefficient to cause maximum deviation, it should act perpendicular to the needle. You remember on easterly or westerly heading, the blue and red pole of the ship are at right angles to the magnetic field of the earth, or they are acting perpendicular to the compass needle, giving maximum deviation. Now basic principle which is followed in correcting the compass is to cure like with like. Now what do we mean by curing like with like? It means permanent magnetism deviation are cured or corrected by using permanent magnets. Induced deviations are corrected or cured using induced magnet. So permanent is corrected with permanent, induced is corrected with induced. So same thing is mentioned here. Permanent deviation is cured or corrected with permanent magnets. Induced deviation is corrected with induced magnetism. So permanent B, which is caused by ship's fore and aft horizontal permanent magnetic field, is therefore corrected using fore and aft permanent magnets which are placed horizontally. Now these magnets are so placed as to produce a permanent magnetic field at the compass location exactly equal and opposite to that of the ship. Now how we do that? Let us try to understand using this diagram. In this diagram, we see the same ship which we discussed for deviation. This ship is having a blue bow and it is having a red stern. Now you see the binnacle, this is the binnacle, and the compass is fitted at this particular location. Now these blue and red poles, why were they generated? Because this particular ship was constructed on a southerly heading, and during its construction it acquired these permanent poles. Now because of this blue and red poles of the ship, a magnetic field is generated. You can follow the laser pointer. The laser pointer now is moving on the magnetic field generated by the permanent poles of the ship. You see the magnetic field lines come out of the red pole and they go back into the blue pole. That is how the magnetic field lines are acting at the compass location. So what we do to correct it? We use fore and aft permanent magnets. We place them in the binnacle just below the compass, and we place them in such a way that their poles are opposite to the poles of the ship. So we had the blue pole at the bow. When we place these correctors, we place the blue pole towards the stern. You see, we have red pole of the corrector magnet towards the bow. So when you place these magnets in the binnacle, they generate a correcting field. Right now the laser pointer is on the correcting field. and you can see that the direction of the correcting field is opposite to the direction of the deviating field. So when you place these corrector magnets in the binnacle in the fore and aft direction with their poles opposite to the poles of the ship. Forward of the ship had a blue pole, forward of this corrector has a red pole. So with the poles opposite to the poles of the ship, they generate a opposite field, thus correcting the deviation caused because of permanent B. Is that clear, beta? Any doubts? Very good, beta. Great. These magnets which we use, the fore and aft magnets, they are bar magnets of circular cross section. They are 8 inches long and they come in two thicknesses, either 3 by 8 inches or 3 by 16 inches diameter. So where more powerful magnets are required, we use the thicker ones, that is 3 by 8 inches, or where less powerful correctors are required, we use 3 by 16 inches diameter magnets. The size is decided by the compass adjuster. Once the ship is constructed and it goes out for sea trials, the compass adjuster checks the magnetism of the ship and decides upon whether he wants a thicker corrector or a thin corrector magnet. Slots are provided in the binnacle below the compass and the magnets are placed 2 in a row side by side. So when we place these corrector magnets, they are always placed in pairs. So one of the magnets is slightly to the starboard of the compass, another magnet is to slightly port of the compass. They are always placed in pairs. Now why are they placed in pairs? The reason for that is exactly in the middle of the binnacle or exactly below the compass, you have a periscope which is going into the wheelhouse. It is with the help of the periscope that you are able to see the magnetic compass at the helmsman location from the bridge. So because of this periscope, we cannot have the corrector magnet exactly below the compass location. Let me show you a actual binnacle now where these magnets are placed. Let me show you these fore and aft permanent corrector magnets in the binnacle. You can see a diagram of the binnacle. We have the compass here and we have these spheres which are fitted in the outward ship direction. Exactly below the compass, you see one particular pipe is going down. This is the healing error pipe. We have the periscope pipe also along with this, and you can see these are the fore and aft magnets which are fitted in the binnacle below the compass. And you can see these are placed 2 in a row side by side, one on either side of this pipe or the healing error corrector bucket. We can also see outward ship magnets placed inside the binnacle. These are used to correct permanent C, which we will be seeing later. Now, these magnets are accessed using plates. Plates are fitted on the binnacle. You can see these plates here. These plates are removed and then these magnets can be accessed and placed as required. Clear, beta? Understood? Very good, beta. Great. So that completes the permanent B coefficient. Now the next one which we have is induced B. So let's take a break here, beta. Let me stop the presentation. Let's take a short break and then we meet again for induced B. See you after the break.
Yes, sir. Check. Check.
हाँ भाई ठीक है ब्रेक है अभी 5 मिनट का।
ओके भाई।
Okay, beta, are you back? चले आगे? चले बेटा आगे वापस?
हाँ सर, आ गया सर.
Yes, sir.
Okay, all right. Let's go, beta. Now we will see the induced B, the second part of coefficient Bravo, induced B. Let's go. Let's now move on to the second part of coefficient B, that is induced B. Induced B is caused by horizontal fore and aft magnetic field at the compass due to the induced magnetism in the vertical soft iron forward or aft of the compass. So you see, again it is a horizontal fore and aft magnetic field, but it is generated because of induced magnetism in the vertical soft iron forward or aft of the compass. Let me show you how it is generated. The vertical soft iron which we have on ship could be the forward mast, it could be a crane, it could be the funnel, or it could be a aft mast or a crane aft of the compass location. Now all these vertical structures will be induced by the magnetic field of the earth, by the vertical component, Z component of the earth. If this particular ship is in northern hemisphere, the lines of force go vertically downwards, so they will be entering from the top end of the VSI and leaving out from the bottom end of the VSI. So the top end where they are entering gets a blue polarity, and the bottom end where they are leaving out gets a red polarity. So you see all the top poles of the vertical structures are blue. The top pole of the funnel is blue, the top pole of the forward mast, aft mast or the cranes is blue. The bottom poles of all these vertical structures are red poles. Now out of these two, what affects our compass is the pole which is closer to the compass, and in this case the top of the poles, which are the blue poles, are almost in line with the magnetic compass and they affect our compass. If the same vessel goes in the southern hemisphere, now in the southern hemisphere the magnetic lines of force come out of the Earth's surface. So you see, with the same vertical structures in the southern hemisphere, the polarity is going to change. The lines will now enter from the bottom of these vertical structures, giving it a blue polarity, and it will come out from the top of these vertical structures, giving it a red polarity. So these being induced magnets, their polarity changes when the vessel changes from northern hemisphere to southern hemisphere. So as we discussed just now, the compass is generally situated at level with the top poles of the masts and the funnel. The top poles therefore affect the compass more as compared to the bottom poles of these vertical soft iron structures. We are aware that the compass is affected by that pole of the magnet which is closer to it. So we can see that the compass is situated in line or at level with the top poles of these vertical soft iron structures. So the top poles affect the compass more and the bottom poles, being far away, do not affect our compass. Second thing to note is that funnel is the largest vertical soft iron structure on board. We may have the masts, we may have the cranes, aft mast, but the amount of steel which is used in construction of the funnel is much more, as well as the size of the funnel is much more as compared to the size of masts or cranes. So therefore, funnel affects our compass most predominantly among all the vertical soft iron structure. So the effect of the funnel being the most predominant is considered mainly for induced B. Moving ahead now. Let us now try to understand the deviation generated by induced B coefficient. So you can see the ship on cardinal and intercardinal headings. And we can see the compass needle. The north end of the needle is red, the south end of the needle is blue. And we have a ship having a vertical soft iron aft of the compass, abaft of the compass. And as we just now discussed, that out of all the vertical soft iron structures, the funnel has the largest structure, the maximum amount of steel which is used in the funnel as compared to the mast, the crane. Also, funnel is having the biggest size among all the vertical soft iron structures on board. And thirdly, the funnel is also located very close to the compass. The top of the funnel is almost in level with the compass card. And being the largest structure and also being very close to the compass as compared to maybe the forward mast or the cranes, it gives us the most predominant effect. Now, another important thing to understand here is if we have a vertical structure forward of the compass and a vertical structure aft of the compass, they are going to cancel out each other. Two vertical structure forward and aft of the compass are going to cancel out each other. But as far as the funnel is concerned, the funnel is abaft of the compass and there is no comparable structure forward of the compass in comparison to the size and the amount of steel used as is done in the funnel. So that's why you see that in this deviation diagram, the funnel is considered as the vertical soft iron structure on board, and this particular ship is considered to be in the north hemisphere. In the north hemisphere, the magnetic lines of force, they go vertically downwards into the surface of Earth. So they enter from the top pole of the funnel, giving it a blue polarity, and they leave out from the bottom pole of the funnel, giving it a red polarity. The bottom pole being far away from the compass doesn't have much effect, whereas the top pole is the one which affects our compass. So let's now see the deviation generated because of the funnel. With the ship heading north, we have this blue pole at the top of the funnel abaft of our compass. It is exactly south of the compass needle. Even though the blue pole tries to repel the blue end of our compass magnet, it is not able to do that because the magnetic field generated by the funnel is much weaker as compared to the magnetic field of the Earth. Now the compass is pointing northwards, the red pole of the compass is pointing northwards because of the Earth's magnetic field. And the funnel's blue pole is trying to rotate the compass and turn it by 180 degrees. It wants the red end to point southwards where the funnel is, but it is not able to do that because the magnetism of the funnel is much weaker as compared to the magnetism of the Earth. Now then the ship goes on a northeasterly heading. On the northeasterly heading, the blue pole of the funnel comes to southwest of our compass needle. Now when it comes southwest of the compass needle, it is no more aligned with the magnetic field of the Earth, so it starts repelling the south end of the compass needle, and the compass needle turns anti-clockwise, or a westerly deviation is generated. When the ship goes to easterly heading, on a easterly heading, the blue pole of the funnel is at right angles to the field of the earth. It is exactly west of the compass. It is right angles to the field of the earth, and it provides or generates the maximum deviation. This blue pole of the funnel attracts the red end of our compass magnet and repels the blue end of our compass magnet, generating maximum westerly deviation. When the ship goes on southeasterly heading, in a southeasterly heading, the funnel blue pole is to the northwest of our compass, and again the blue end or blue pole of the funnel attracts the red end of our compass needle, and a westerly deviation is generated. But the westerly deviation now starts to reduce. Why the westerly deviation reduces is because the blue pole, which is generating this deviation, is now no more at right angles to the field of the earth, and it has started coming in line with the earth's magnetic field. Any pole, when it generates deviation, it generates maximum deviation when it is at right angles to the field of the earth. So when it is at right angles to Earth's magnetic field, it will generate maximum deviation. And when it is aligned with the Earth's magnetic field is running north-south. So when a pole comes north or south of the compass needle, it does not generate any deviation at all. So when the ship goes on southerly heading, the blue pole of the funnel comes exactly north of our compass, north of the compass needle. And since it is aligned with the magnetic field of the earth now, it does not generate any deviation at all. So no deviation on south heading. When the ship heads southwest, the blue pole is to the northeast of the compass, and this blue attracts the red pole of our compass magnet, the compass needle, and it generates a easterly deviation now. So easterly deviation is generated. When the ship moves on 270 heading, ship is heading west, then the blue pole of the funnel is now exactly east of our compass needle. So at this location, it is at right angles to the Earth's field. It attracts the red end of our compass needle and repels the blue end of our compass needle. The compass needle turns clockwise and generating a easterly deviation. At this point, the easterly deviation is maximum. What is the reason for that? Because the pole which is generating the deviation is at right angles to the magnetic field of the Earth. When the ship goes on northwesterly heading, this blue pole has come southeast of the compass needle, and it now repels the blue end of our compass needle, generating a easterly deviation. But the amount or magnitude of the deviation is reduced now because the pole is no more at right angles to the Earth's field, and it has started coming in line with the field of the Earth. So we can see that the deviation which is generated is semicircular from 000 to 180. The deviation generated is westerly. A westerly deviation is generated, and from 180 to 360, a easterly deviation is generated. Maximum deviation is generated on easterly and westerly courses, and zero deviation is generated on northerly and southerly courses. So you can see it is proportional to sine of the compass course. Sine 90 or sine 270 has a magnitude of 1, and sine 0 and sine 180 are 0. So it is proportional to the sine of the compass course. Now, how does this IB affects the directive force? You see, with the ship heading in the northerly direction, this blue pole of the funnel is opposite to or is opposing the south pole, which is of red polarity. The south pole of the Earth is of red polarity. The pole on the funnel is blue polarity. So with these poles having opposite polarity, it reduces the directive force. When the ship is heading south, then the blue pole of the funnel and the blue pole of the Earth, they match, increasing the directive force at the compass location. So whenever the ship is on a northerly component heading, northeast, north or northwest, the directive force is reduced because this funnel's blue pole is southward of the compass, giving or reducing the directive force. Whereas when the ship is on a southerly component heading southeast, south or southwest, the directive force is increased because the blue pole of the funnel is north of the compass needle. Any doubts coming in, beta? Clear? Very good, beta. Great. Let's move ahead. Let's now discuss the correction procedure, the concept behind the correction of induced B. We use like cures like principle. That means permanent deviation is corrected using a permanent magnet. Induced deviation is corrected using a induced magnet. Now, since this induced B is generated because of magnetism in the vertical soft iron, we will use the soft iron for correction of IP. So vertical soft iron is used for correction and it is used in the form of Flinders bar. The value of induced magnetism depends upon the length of the soft iron. Hence, the length of the Flinders bar is varied as per the correction required. Now, when we are doing a correction with permanent magnets, we can easily control the magnitude of correction by increasing or decreasing the number of magnets used. But what to do in case of a soft iron or in case of induced magnetism? The magnetism which will be induced is not in our control. It is dependent upon the magnetic field of the Earth. So how can it be controlled or magnitude changed? Now that can be done by changing the length of the soft iron which is used as a corrector. The longer the soft iron, the more induced magnetism it is going to attain or have. So if we require a greater correction, then we use a longer Flinders bar, and in case the correction required is minute, then we can shorten the length of the Flinders bar as per our requirement. Moving ahead now. Now going more into analyzing the Flinders bar. The Flinders bar is placed inside a brass case. It could be a brass case or it could be a plastic or it could be any material which is non-magnetic. Now all the items which are used close to the magnetic compass in the binnacle, even the nails and screws which are used, they are made up of non-magnetic material. Only the correctors which we are using, they are either the permanent magnets or they are the soft iron rods or soft iron structures. Other than that, all the other parts of the binnacle are made up of non-magnetic material. So Flinders bar is placed inside a brass case or a non-magnetic case, and its length is 610 millimeters. And this casing is attached to the binnacle. The soft iron bars which are put into this casing are provided in pieces, It is not that they provide us with a single length flinder bar, which is 610 millimeters long. What is provided is they break up the 610 millimeters into small portions or small parts so that the compass adjuster can use the required parts or the required length of the flinder bar. So I'll explain to you how this is used. Now the flinder bar which is provided is in pieces. The first piece is 305 millimeters. Then the next piece is 152 millimeters. Then we have a piece of 76 millimeters, 38 millimeters, and then there are two pieces of 19 millimeters, making a total of 610 millimeters. Now, why are these provided in small pieces? Because as we just now saw, to vary the magnitude of correction, we can change the length of the flinder bar. So once these pieces are provided to us, we can use whatever pieces we require, and the other pieces can be kept as spare. So this is the approach behind providing the pieces. Now, how are these pieces utilized? When a flinder bar is supplied on the ship, along with these soft iron bars of these dimensions, a complete set of wooden pieces of the same dimensions are also provided. So you will have wooden pieces of all these dimensions along with the soft iron bars also provided. Now this is given to help us vary the length of the soft iron as per our requirement. Now on a ship which has a very big funnel, huge funnel, let us say we have a VLCC and it has got a huge funnel. Now if the funnel is quite big, that tells us that the induced P on that particular ship is going to be substantial. So we may require a flinder bar close to maybe 500 or 600 mm. Now on another vessel which has a very small engine and has a very small funnel, the correction required may not be very much. So we may require just about, let us say, 100 or 200 millimeters of the flinder bar. So these wooden pieces help us to vary the dimension or length of the flinder bar. Let me now show you how these pieces are placed in the flinder bar. Let me show you with a diagram. Let me explain the use of the soft iron bar and the wooden bar for filling up the flinders bar. So you see this is the flinder bar present on a ship, and this is basically the casing in which the bar would be placed. The maker supplies us a soft iron bar in these dimensions. You see one piece is for 305 mm, the next one is 152 mm, 76, 38, then two pieces for 19 mm. And along with the soft iron bar, he also provides a wooden bar of same dimensions. You see, we have the pieces with exactly same dimensions. So first of all, compass adjuster evaluates what length of the flinder bar he requires. Let us assume that on a particular ship, the compass adjuster has ascertained that he needs to use these two pieces, 305 mm and 152 mm. What he does now is, leaving these two pieces, 305 and 152, 305 and 152, he will pick up all the other pieces of the wooden bar. So you see all these pieces with a green tick mark, other than the ones which are required. Other than 305 and 152, he will pick up all the wooden pieces, 76, 38, 19 and 19. And he will pick and drop these pieces in the flinder bar casing. So let us put these pieces here. You see all these four pieces coming here. 19 mm, 19 mm, 38 mm and 76 mm. All these four pieces coming here. These are the wooden bar pieces. Now once these wooden pieces are placed at the bottom of the flinder bar casing, He now picks up the required soft iron pieces, 152 mm and 305 mm, and he drops these pieces into the flinder bar. So you can see this 152 mm piece and the 305 mm piece dropped in the flinder bar, and now you can see the top end of the soft iron bar will be in level with the compass card or as required. So the bottom portion is filled using the wooden pieces, thus making the flinder bar correction. Is that clear, beta? Any doubts coming in? Great, beta. Very good. Let's move ahead. Now, when we are putting the flinder bar, the bar is so adjusted as to keep the top pole in level with the compass card. It should be so placed that the top pole of the flinder bar should be in level in the same horizontal plane as the compass card. So as IB is caused by the funnel which is aft of the compass, the flinder bar is placed forward of the compass to compensate its effect. The basic concept is, as you can see in this particular diagram, we have the binnacle here. The compass is located at this location. We have the funnel abaft of the compass, and it is getting induced by the Earth's magnetic field. Right now the ship is in the northern hemisphere. In the northern hemisphere, the magnetic field lines, they go down into the surface of Earth. So that's why you see the top pole of the funnel is blue. This blue pole affects our compass and generates IB, induced B. Now what have we done here is we have placed a flinder bar forward of the compass. The flinder bar is also made of soft iron. So when you place this flinder bar, this also gets induced by the Earth's magnetic field and generates a blue pole on the top end. Now this blue pole forward of the compass cancels out the effect of the flinder bar which is abaft of the compass. Is it clear, beta? Any doubts coming in? Very good, beta. Great. So that completes our coefficient Bravo. Induced B is also completed. So let me show you the...
Sir, one thing I wanted to ask.
Go ahead, beta.
For everything and all this, why are we not considering accommodation as for vertical correction?
Okay. Accommodation will come, beta. It will come in the healing error correction. Accommodation is, you see, basically vertically below the compass.
Okay.
Okay. It's exactly below the compass. So any magnetic field vertically below or above the compass will lead to healing error. We will do that after the coefficients. The next is healing error.
Okay. Understood.
Okay. Let me now show you the location of the flinder bar. Now you see we have the binnacle here. This is the compass bowl. And then we saw in permanent B that we use fore and aft magnet placed in these trays. Now the flinder bar is placed in this housing, you see. This cylindrical housing which is there, it is fitted forward of the compass. So why it is fitted forward of the compass? Because it is compensating or correcting the magnetism of the funnel. The funnel is fitted aft of the compass. On a normal merchant vessel, you will have the funnel aft of the compass. So to counteract it, the flinder bar is placed forward of the compass. You can see the flinder bar in this particular diagram also. This cylinder which you see represents the flinder bar. You can see it is mentioned here. So this is the housing which you are seeing. This is the casing. And in this casing inside we have the flinders bar. Great, beta. That completes coefficient Bravo. So I'm closing down the presentation.
Sir, this is, as you said, is conventional merchant vessel. How about container vessels? Like when they load, the amount of container loaded in a vertical space can be different for every different voyage. So how do they tackle the magnetism of that?
Okay, very good, beta. Very good. अब देखो बेटा, कोई भी शिप जिस पे मैग्नेटिक कार्गो लोड या अनलोड हो रहा है, इट बेस्ट एग्जांपल इज द कंटेनर शिप. इतने कंटेनर्स आ रहे हैं और इतने कंटेनर्स जा रहे हैं. सो एवरी कंटेनर इज मेड ऑफ ए फेरोमैग्नेटिक मटेरियल, सो द मैग्नेटिज्म इज चेंजिंग. Another example could be a roll-on roll-off ship, ro-ro ship. Lot of vehicles are coming in, or car carriers, vehicles are coming in, vehicles are going out. With all those vehicles coming in, the magnetism changes. Every load port, discharge port, the magnetism is going to change. Another example could be the bulk carriers carrying iron ore. Iron ore also has magnetic properties. In all these ships, beta, you will see with each loading and unloading, whenever the cargo gets discharged or loaded, any change in the cargo is going to have a drastic effect on the deviation. So theoretically speaking, every time when you load or unload a cargo, you will have to readjust and recalibrate the compass. But that's not practically possible. So it is taken with a pinch of salt that in all these ships, the deviation curve is going to be too much disturbed. And you could have deviation values ranging from a large value difference. It could be plus minus 20, 25, 30 degrees also. So there's no way that it can be corrected.
Okay, sir. Yeah.
Right. Okay, great. So, और कोई डाउट आ रहा है माइंड में बेटा? एनीथिंग एल्स?
सर मैंने एक जायरो का सर न्यूमेरिकल के लिए ग्रुप में डाला हुआ था.
ओके बेटा, थोड़ी देर रुक जा. मैटर ऑफ कपल ऑफ मोर सेशंस, फिर जायरो पे जा रहे हैं. वी विल डिस्कस इन डिटेल, डोंट वरी.
सर उसमें सिंपल एक क्वेरी था सर. स्ट्रीमिंग एरर के लिए सर जो tan अल्फा इक्वल टू v इंटू cos फोर्स डिवाइड बाय 900 इंटू cos लैट वाला फॉर्मूला है. इंस्टेड ऑफ दैट सर एक lambda इक्वल टू v cos फोर्स डिवाइड बाय 5 pi cos लैट, इसको यूज कर सकते हैं क्या? बिकॉज वी आर गेटिंग आंसर सेम आंसर सर.
Yeah, you can use it, beta. You can use it, but it's a simplified formula. Practically आप इसे use करोगे perfect है, no problem at all. बट एग्ज़ाम में आई वुड रिकमेंड कि जहाँ पे भी आप डिटेल्ड फार्मूला लगा सको तो डिटेल्ड ही लगाओ, बिकॉज एग्ज़ाम में तो मार्क्स चाहिए ना बेटा. आपने अगर ये रिड्यूस फार्मूला लगाया, पीपल कैन कट मार्क्स.
ओके सर, ओके
ओके. मैं बताऊंगा दोनों चीज़ें आपको डिटेल में. कुछ एक क्वेश्चन हैं जिनमें डिटेल्ड फार्मूला लग ही नहीं सकता है. देयर आर सम टिपिकल न्यूमेरिकल्स ऑफ जायरो, सो उनमें हम इसे यूज़ करेंगे. वी विल यूज़ द सिंप्लीफाइड फार्मूला.
ओके सर.
ओके, ग्रेट. ओके, वेरी गुड बेटा. अब मुझे ये बताओ बेटा कि या इट्स वी हैव अबाउट 15 मिनट्स और सो. बोलो बेटा.
Coefficient A.
Coefficient A.
We can say that this is caused by the rod P and rod D that came from the 9 rod.
Okay. Bravo and Delta.
Yes.
Okay, just a minute. Bravo and Delta. Yeah, you can say that, beta. You can say that it is caused by a combination of Bravo and Delta. That's right. मैं आपको दिखा भी देता हूं. मैंने आपको एक कॉम्बिनेशन दिखाया था जिससे कोफिशिएंट ए जनरेट होता है. Now there can be more possibilities also जिनसे कोफिशिएंट ए जनरेट हो सकता है. Let me show you. I'll show you. Okay, so I hope you can see this slide now. You see यहाँ पे 4 ऑप्शंस आपको दिखाई दे रहे हैं, 4 ऑप्शंस. सो जो फर्स्ट ऑप्शन है ये हमने डिटेल में डिस्कस किया था. वी मेड द डेविएशन डायग्राम यूजिंग द फर्स्ट ऑप्शन. एंड इसके बाद और 3 ऑप्शंस हैं. इस तरह के कॉम्बिनेशंस भी अगर होंगे तो कोफिशिएंट ए को जनरेट कर सकता है ये. एंड इन ऑल दीज 4 यू विल सी इट्स ए कॉम्बिनेशन ऑफ ब्रेवो एंड डेल्टा रॉड्स. जिन बच्चों ने रॉड्स नहीं देखी हैं, यू डोंट नीड टू रिमेंबर इट बेटा. वो तो इन्होंने पूछा तो मैंने बता दिया कि ब्रेवो एंड डेल्टा ये रॉड्स हैं. एंड मैंने जो आपको नोट भेजा है उसमें वो रॉड्स की डायग्राम भी है. सो यू कैन से दैट इट्स जनरेटेड बाय ब्रेवो एंड डेल्टा. ओके, ऑल राइट. और बताओ बेटा, और कोई डाउट्स? एनी मोर डाउट्स कमिंग इन?
So for exam purpose, this 9 rod concept, should we memorize it or not?
बेटा करना पड़ेगा, क्योंकि ना ये सवाल 1-2 बार आ चुका है. तो आपको सीधा 10 नंबर का सवाल दे देगा, व्हाट आर द 9 रॉड्स प्रेजेंट ऑन ए शिप. तो आपको डायग्राम बनानी पड़ेगी. नो अंडरस्टैंडिंग, यू जस्ट नीड टू मग अप, मेक इट 2-3 टाइम्स सो दैट यू रिमेंबर इट. एंड ये क्वेश्चन अगर दोबारा आ गया तो आपको इसे बस वो डायग्राम याद कर लो. दैट इज ऑल यू रिक्वायर. ओके. इनकी जो एप्लीकेशन होती थी, द एप्लीकेशन वाज डन इन न्यूमेरिकल्स बेटा. पहले मैग्नेटिक कंपास पे न्यूमेरिकल्स आते थे. दैट वाज बिफोर 2012. ओके. सो व्हेन वी पास्ड आवर एग्जाम दैट टाइम न्यूमेरिकल्स वर आल्सो देयर. तब इनकी प्रैक्टिकल एप्लीकेशन भी थी. नाउ नो मोर न्यूमेरिकल्स, नो मोर प्रैक्टिकल एप्लीकेशन. And you need to just memorize the diagram. You should be able to make the diagram. That's it.
Okay.
Okay. और बेटा और बताओ, मजा आ रहा है मैग्नेटिज्म में अब?
बिल्कुल भी नहीं सर, बस मगअप में लगे.
ओके, डोंट वरी. अभी तो इंटरेस्टिंग चीजें आएंगी आगे. अभी तो कोफिशिएंट्स हो रहे हैं ना. आगे मैं आपको जब चार्ली कराऊंगा, सो उसमें एक बहुत इंटरेस्टिंग क्वेश्चन आता है. एक्सप्लेन द कंबाइंड करेक्शन फॉर ब्रेवो एंड चार्ली, बी एंड सी. नाउ दैट्स ए बाउंसर. उसका आंसर बुक में भी नहीं है. सो दैट्स ए इंटरेस्टिंग क्वेश्चन. फिर उसके बाद डेल्टा आएगा. डेल्टा में भी एक इंटरेस्टिंग क्वेश्चन आएगा. वो आपको बोलेगा कि एक शिप है, उस पर जो स्फीयर्स हैं वो ऑथवर्ड शिप नहीं लगे हुए हैं. दे आर टिल्टेड बाय सम 10 डिग्रीज और सो. So explain the fundamental behind it, analyze why it is done. उसका भी आंसर कहीं नहीं है, not there anywhere. So आगे इंटरेस्टिंग क्वेश्चंस आएंगे और. ओके, ग्रेट. और बेटा, और एनी मोर डाउट्स? ओके, ग्रेट. सो अल्फा एंड ब्रेवो इज डन. कल जो हमारा सेशन होगा इसमें बेटा होपफुली चार्ली डेल्टा करेंगे. और जो मैंने ये आपको एक कपल ऑफ क्वेश्चंस बताए ना, टिपिकल क्वेश्चंस, ये भी साथ में ही पिकअप कर लेंगे. सो वी विल डू दीज टिपिकल क्वेश्चंस आल्सो. एंड इसके बाद जो नेक्स्ट सेशन होगा आफ्टर टुमारो, दैट नेक्स्ट सेशन वी विल कंप्लीट इको, लास्ट कोफिशिएंट, दैट्स ए वेरी स्मॉल कोफिशिएंट, एंड द कंपास करेक्शन. Along with that, we will pick up some typical questions which come in our exams. So I'm seeing in next 2 sessions, we should be covering up the magnetic compass, at the most 3. Okay.
Okay, sir.
Okay, all right. So shall we close out for today, beta?
Yes, sir.
Okay, great. So I'll see you tomorrow and we'll continue. Till then, bye-bye.
Bye-bye, sir. Have a nice evening, sir.
Good night, beta. Bye-bye. Good night.